Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, I'll go through this year 11. So this is a 3-year curriculum for the triple sciences, pure chemistry, Cambridge International O-Level. So this is quite an early exam, early in the year, but this will encompass or pretty much cover the entire O-Level syllabus, the entire equivalent syllabus to IGCSE or GCSE, 14 to 16 years old chemistry, pure chemistry students all around the world. 1 hour multiple choice paper as usual for this paper 1. In this first question, so we have these questions asking us on choosing apparatus depending on the measurement that's given. So we know the measuring cylinder can measure volume of solution as well as volume of gas if you have an inverted measuring cylinder submerged in water. So we have this 25.0, we can see that this is fairly very accurate, and we don't typically associate this sort of accuracy with a measuring cylinder. That is not appropriate at all. Pipette, on the other hand, is a fixed volume, so it can measure fixed volume accurately. But if you had done any titration before in the lab, you would know that the question always said 20.0 cm cube, 25.0 cm cube pipette. Of course, these are volumetric pipette as stated in the new 2023 syllabus. Volumetric pipette measures volume accurately. So yes, you can measure things like 30.0 because they do definitely come in various sizes other than these two, but they don't come in specific sizes with these 0.7 cm cube like these. Again, that would not be appropriate for a pipette. A gas syringe can measure volume, so that is fine, and it's a volume of gas, and that is also fine. So why is that not fine? That C should be the answer, because looking at burette, this is 80 cm cube, whereas usually we associate this with a 50.0 cm cube burette. So this is fairly accurate to 1 decimal place for your titration. But then of course you can measure 80.0 if you want to. You just need to do it twice, like 40.0 and 40.0, or you can do 50.0 from a burette and then another 30.0, but you don't get this sort of not very accurate result because you're just looking at without the 1 decimal place there. So that is not going to be appropriate for you to use a burette. You can if you want to, but it's not going to be this inaccurate. It's going to be much more accurate there. Okay, so D cannot be the answer there. Question part 2, so we have a liquid X, so you have a liquid X, so the fact that it's there means that there's only one liquid X is distilled from the mixture using this apparatus shown. This is a simple distillation because it does not have a tall distillation column. Distillation column is that thing that is sticking out vertically that allows you to have a better separation of the stuff to be separated, and you don't have that column, therefore it's not fractional distillation. We have this apparatus which is called a condenser. So you have water in from the bottom and water out from the top. As this boils, you're going to get liquid going to gas inside there, and then you're going to get gas going back to liquid in the condenser here. So 2 particular processes. The hot vapor goes up, and then the vapor gets cooled down as it loses energy, and you collect this as a liquid. It's a liquid X, so it's just 1 particular liquid. During the distillation, the thermometer reads a range of temperature. This is a bit strange. This is over a range. It makes me suspicious that this is a mixture perhaps, but then the fact that they told us that it's a liquid, so it's quite strange that it doesn't have a fixed melting point, because usually pure substance will have a fixed melting point. So what information is correct? Correct. The liquids in X may or may not be miscible. This is a bit unusual. I don't know what A means, but what is B? X is a mixture. X cannot be a mixture because you already said a liquid is distilled out. A liquid is 1, so it cannot be a mixture there based on a liquid. So the definition of a there simply meaning 1, so it's not a mixture. They must contain 2 liquids, so again I guess it's come down to a liquid, meaning 1, so not really C there. X must have been obtained from the fractional distillation of crude oil. Not really, because you could be other fractions. And also, what do we here? X must have been obtained. Well, you do know that you have other fractions such as natural gas at the very top used for home cooking, and then of course you have liquid petrol used in cars, and of course you have bitumen at the further down at the bottom of the fractionating column used to make rod there. So really D cannot be the answer, leaving us behind A as the only possible answer by elimination. Question 3, we have an aqueous solution. The fact that you have aqueous and the fact that you have solution, these are soluble. We are looking at a solution that is see-through without any insoluble stuff. We have a salt, and this salt, when we added it to X, we get a precipitate. So the fact that we have aqueous plus aqueous, and then we get a PPT, this is insoluble because the fact that it's a PPT is insoluble. This reaction is what you call precipitation type of reaction. So we need to know about solubility rules. Solubility rules are part of salt preparation topic in the curriculum. So you redissolve that precipitate when more of X is added. So what could solution X and salt be? Well, if you look at A, you're going to get the Ag plus from the silver nitrate. You got to know that all nitrates are soluble, including silver nitrate solution. And then you get hydrochloric acid. Then you get a test for chloride, which is silver chloride precipitation. This is a white precipitate. It's in the paper 3. This is test for chloride ion. Bromide ion will give you silver bromide, Ag plus Br minus. AgBr is cream precipitate. Agi, on the other hand, will be a yellow precipitate. The next one is your test for sulfate, so barium 2 plus from the barium nitrate, which of course all nitrates are soluble, so it's a colorless solution there, not containing any transition metal. So with the sulfuric acid, it's the sulfate that will actually give you the white precipitate as the test for your sulfate there, giving you barium sulfate, a solid. This is a white precipitate. This is your test for SO42 minus. The table of results for qualitative analysis are never provided. So it says it will redissolve when more of X is added. It doesn't redissolve. These two are insoluble white precipitate. We're now left with C and D. Now we know that with C, test for copper 2 plus. So this is Cu2 plus, and this is using sodium hydroxide. We do know that we get a pale blue precipitate. That will be the precipitation of your copper 2 hydroxide, Cu2 plus, OH minus, LCM. The objective of getting to the formula is to look at the value of the charges, which is 2 and 1 respectively, based on the charges of the ion. Cross multiply in order to get this idea of how many of this ion you need. Well, you will need 1 of the copper 2 plus, 1 of this, 2 of the OH minus, because minus 1, cancel out the plus 2. This is the formula for copper 2 hydroxide, pale blue precipitate. But this one is insoluble in excess sodium hydroxide. It can only dissolve if you have excess aqueous ammonia to give you a dark blue solution. So again, out of elimination, we're just left with D, and we can see that D is actually the test for zinc 2 plus ions. So we do know that we get a white precipitate, which is basically your zinc hydroxide. And with the zinc hydroxide white precipitate in excess of sodium hydroxide, just like aluminium hydroxide giving you a white precipitate, this is going to redissolve in excess sodium hydroxide giving you this stuff. And you're going to have 2 of the sodium ions, and this will be aqueous. This will be colorless solution. In the practical table of results, zinc 2 plus ions will form a white precipitate with aqueous sodium hydroxide at first, but then in excess of sodium hydroxide, it will redissolve to give you a colorless solution. All sodium salts are soluble in water. There's another solubility rules. All sodium plus salts are soluble in water there, and that's essentially the information there, giving D as the only possible answer. Question number 4, diffusing the fastest at the same pressure. So rate of diffusion, the fastest means you're looking at the lightest. So that means the smallest MR, because MR is to do with your masses. And then the other one, of course, is to do with highest temperature, because your kinetic energy will be higher at higher temperature. You can move faster, you can diffuse faster. We are looking at 50 degrees Celsius as there's a higher temperature. So A and C are out. And we then look at the MR of nitrogen, which is a diatomic molecule. So 14 times 2, that's the relative atomic mass of nitrogen, times 2 is 28. And then we get the MR of oxygen, which is another diatomic molecule. It's going to be 16 times 2, which give me 32. So since this is lighter compared to this, lower mass than that, therefore the nitrogen is going to diffuse faster at this temperature compared to oxygen at this same temperature. So talking about diatomic molecules, nitrogen with 2,5 electronic configuration. Nitrogen really only want to share 3 electrons in the outer shells. To complete the electron outer shell, they form triple covalent bond. Oxygen with 2,6 electronic configuration. Oxygen form double covalent bond. This is 2 atoms covalently bonded together. These are what you call diatomic molecules. We have around 78% nitrogen in the atmosphere as part of the composition in dry air. We have around 21% of oxygen as part of the composition in dry air. These are part of environmental chemistry in the syllabus. Question number 5. We have this diagram that shows the outer shell electrons. How many electrons you have in the outer shells? That will tell you your group number. So here we see these are 1, 2, 3, 4, 5, 6, 7. So there are 7 outer shell electrons. Therefore, we are looking at group 7. So VII, Roman numerals stated in the periodic table. Then we have Q. We see 2 outer shell electrons. We are tempted to think about group 2, perhaps. That the sulfate of Q is insoluble. The sulfate of Q is insoluble. If you think about the solubility rules of sulfate, we say all sulfates are soluble except for lead 2 sulfate, Pb2 plus, SO4 2 minus, barium sulfate. We saw the test for sulfate in the practical production of this white precipitate with aqueous barium chloride or aqueous barium nitrate. We also have calcium sulfate. Having said that, a lot of the other group 2, they might be soluble, but they are very sparingly soluble. This one say insoluble. This one also say element R, which is this one, the group 7, is gaseous at room temperature and pressure. We know about group 7 element, F2Cl2 Br2I2. So Br2 is a liquid at room temperature and pressure, as it is one of 2 liquids in the whole periodic table, the other one being metallic mercury in the transition metal series. I2 is a solid, these 2 are gas. Looking at these, we are looking at relative atomic mass of R. So I don't know why I just circled that, but relative atomic mass of R. So this is for one atom, not for the molecule. So this is how they exist as an element. So you have things like chlorine sharing 1 electron to complete the outer shell, as they already have 7 electrons in the outer shell, and now you're just left with 6 more electrons which are not used for bonding them. Okay, so single covalent bond like that. So really we're looking at chlorine and definitely not bromine. These 2 are for bromine, and therefore we're looking at that as because these are gas, so it could be fluorine or chlorine. They didn't show for fluorine, they would only show for chlorine there, so B and C must be out. So between A and D, so the sulfate is insoluble. I would imagine that I would go for magnesium sulfate, because based on what we know about this sulfate, and also we know that group 2 sulfate, if you have used magnesium sulfate in the lab before, magnesium sulfate is not very soluble in a large amount actually. Hang on, let me think about this. This is a tricky one. Do we go for this? 56 is quite unusual, isn't it? 56 is definitely for iron. Why in the world would they give us iron? They didn't tell us it's colored. They don't mention about it being colored, so I don't know whether it's a colored compound. I wouldn't know if it's transition metal or a group 2 metal, which is magnesium. So I would personally go for magnesium simply because we know that magnesium sulfate, even though it is soluble, but then it's not really that soluble in a large amount. But if you go for iron sulfate, I can tell you one thing is that things like iron 2 sulfate, Fe2 plus, SO4 2 minus, FeSO4 is soluble in water. We do actually use this in redox titration. We think about redox titration. You are doing titration of a solution of iron 2 plus with your acidified KMnO4, the purple color oxidizing agent. So it's not like you haven't used it before. You did not do titration with a solution as solid. You did it with solution as solution. So iron 2 sulfate is soluble in water. It said this is insoluble. I really wouldn't go for the iron. Therefore, I would go for the magnesium there. Question 6. Which one about iodine atoms and also iodine ions are correct? So the atom itself will have something, comma 7 because it is a group 7 element. It has 7 electrons in the outer shell. And the I minus will have something, comma 8 because previously if you look at the outer shell, you will have 7 electrons in the outer shell like that. And now you will have 8 electrons in the outer shell because you have already gained 1 extra electrons. Having gained 1 extra electron is going to be -1 charge like that. When they say they are both isotopes, they are not because isotopes refer to different atoms of the same element, same number of protons, but different number of neutrons. If they have the same number of protons, and we also say they are different atoms, so the fact that we say that different atoms, we don't say ions, okay, so that means that we have got to have the same number of electrons as well because they're atoms. The number of electrons must balance the number of protons there. It's actually the neutrons that are different. The number of neutrons that are different. For isotope, A cannot be the answer. They undergo the same chemical reactions? Not really, because if you look at the number of electrons, this one has 1 extra electron. Because of your 1 extra electrons, your outer shell is already completely filled. You're going to become less stable. Therefore, we said that one is different electronic arrangement, different number of electrons, different electron arrangement. And therefore, you're going to have different reactivity as a result of different electronic configuration. Same number of protons? Yes, because they are essentially still the exact same the exact same element. I beg your pardon, the exact same element. Therefore, they have the exact same number of protons, same physical properties. Not really. I mean, one you have 0 charge versus one which has -1 charge there. So D definitely is not the answer there. Question number 7, we have this isotope chlorine 35 and chlorine 37. What is this 35.5? In the periodic table, they have been very kind. They show you as relative atomic mass. In the theory part of the syllabus, you're also defining it as part of the syllabus. Candidates should be able to define this as the average mass for all the isotopes because your elements could have more than 1 isotopes, and for all isotopes of a particular element, and this one is relative to this scale, which is 1/12 times the mass of one atom of carbon-12. This is how we write carbon-12. This is pronounced as chlorine 35, chlorine 37. So to get this 35.5, we can see that the average is going to be lower than 36. If you have a table that have a number scale actually, 35 and 37 like that, and then your midpoint, this is your midpoint. Your midpoint in the middle is going to be 36, but your average actually lie lower than your midpoint, halfway in between 36 and 35. This means you have a lot more. You have a lot more of 35 than 37. So you have more 35 than 37, more of chlorine 35 than chlorine 37. That is all about averaging. So A is wrong, B is wrong. If we have 50-50, then how do you work out relative atomic mass? It's going to become halfway in between. That means if you have 50% of chlorine 35, if you have 50% of chlorine 37, it's going to give you the relative atomic mass of 36, and it's not. Instead, it is like that. In the new 2023 syllabus, students are expected to actually measure or calculate the relative atomic mass like this. So you're going to have 75% there, and then you have 25% there. And what they give you on the x-axis would be mass over charge. This is in the mass spectrum, mass spectrometry. I mean, the machine is called mass spectrometer. The result is called mass spectrum. This is chlorine 35. This is chlorine 37. So how do you work out relative atomic mass? It's going to be 35, which is the mass number, this one, multiplied by your abundance, which is 75/100. And then you add it up with the other one, which is going to be 37 multiplied by 25%. And as you Put that into your calculator. 35 times 75 divided by 100. You add it with 37 times 25 divided by 100. You get exactly 35.5. Or you could do 35 times 75 plus 37 times 25. The whole thing dividing that by 100 is the same mathematics that should give you this relative atomic mass there. Question number 8. What is the nucleon number? In the syllabus, the nucleon number is basically the number of protons plus the number of neutrons. In the international standard notation, which is basically not in the middle, like in the periodic table, we have the smaller number at the bottom. This smaller number at the bottom is called the number of protons because that represents the protons or the atomic number, tells you the number of protons there. Whereas this number on the top left in the international standard, that is your nucleon number, also known as mass number, which of course come from the sum of the number of protons and number of neutrons. These two have a relative atomic mass of 1 and 1 respectively. This is basically just reading from this notation international standard, nucleon number, not neutron number. To get the neutron number, you can do 235 minus 92 there. Question number 9, we have silicon dioxide. Silicon dioxide has a giant structure. They don't tell you what structure it is, it's just giant. But silicon dioxide is SiO2. If you sketch out the structure, as stated in the syllabus, as part of giant covalent structure of silicon dioxide, silicon 4 oxide with graphite, with diamond. Each silicon is bonded to 4 oxygen, and then each oxygen is bonded to 2 silicon because oxygen form 2 covalent bond, and then silicon have other additional bond in this 3-dimensional framework. Each silicon form 4 covalent bond to 4 other oxygen. Each oxygen form 2 covalent bond to 2 silicon there. Which property? We're looking at property. So good conductor of electricity? Not really. I mean, like diamond, it does not have free electrons. We don't talk about ions because these are giant covalent structure. We don't talk about ions. We say no free electrons to conduct. So A is wrong there. A high melting point, yes, because you have many strong. Strong is one word, one adjective word, and because you are breaking many strong covalent bonds to be broken for melting, you need a lot of energy. If you need a lot of energy, you need very, very high temperature, therefore high melting point there. As for reaction with hydrochloric acid, it doesn't really do that. You don't really have to know this, but SiO2 is what you call acidic oxide, as it is oxide of non-metal. You know about oxide of phosphorus, oxide of sulfur, they are all acidic oxide. Acidic oxide doesn't react with acid, so no reaction there. Soluble in water? Not really. SiO2 is a component of white sand. So if you have seen white sand, you will know that sand doesn't dissolve in water. That is just insoluble in water there. Question number 10. So element X and Y react to form compound XY. Y has more electrons in its outer shell. Outer shell means valence shell, your outermost shell furthest away from the nucleus than element X. Now X and Y conduct electricity in the molten state. This suggests that XY is ionic. It's an ionic compound, so therefore what is your structure? You're going to have giant ionic lattice structure where you have alternating cations and also anion like this. And then we don't have any free electrons because the electrons have been transferred from the metal to the non-metal. So this is your cation, positive ion, and these are your anion, negative ion. Definitely we're looking at ionic bonding there, not covalent. Now we're looking at X has more electrons in its outer shell. So sorry, X has lesser because X going to Y across a period. If you go from left to right across a period of a periodic table, Y is on the right hand side, and if Y is on the right side, it has more electrons because your group number increases, therefore you have more and more outer shell electrons compared to X, which is on the far left, so that means they have got lesser electrons. In total, what actually happened is you're going to transfer the electrons from the metal X to the non-metal, which is on the right hand side, Y. So from X to Y, and we don't talk about sharing, we talk about donating. So basically X donate to Y, Basically, we could have done that without even interpreting the information, because ionic doesn't involve sharing electrons. Ionic involve transfers of electrons, where the metal loses the electrons and the electron get transferred to the non-metal, leaving behind no electrons that are delocalized, because all the electrons transferred must be balanced out. That's why we have ionic compounds of slightly different formulation there. Question 11, we're looking at the most single bond. The most, that means you got to count the number of single bonds and which one has the most. Well, you got to draw it out. So for A, if I draw out this molecule, it's a carbon-carbon single bond, because each carbon forms 4 covalent bonds. As carbon is in group 4, 1, 2, 3, 4, it shares 4 electrons to form 4 covalent bonds. For B there, this is ethanol. So draw all the bond, especially the O and the H single covalent bond. Oxygen is group 6. If you are group 6, you have 6 outer shell electrons. You just want to form 1 and 2 covalent bonds because you share 2 electrons to complete the outer shell there. Each carbon, 1, 2, 3, 4. Each carbon, 1, 2, 3, 4 there. Well, we got to see for the next one, ethanoic acid as part of carboxylic acid topic. So, oops, not there, because carbon there already form 1, 2, 3, and 4 covalent bond. And last but not least, we have this thing, which is actually another alkene. If you see here, this is CH, and that means there must be a double bond there, because if you don't have the double bond there, let me show you what I mean. If I don't have the double bond there, if I just put in all the hydrogen, I follow the structure CH3, CH3, CH, CH, CH2, but then this carbon, 1, 2, 3, 4 covalent bond. But when you go to the next carbon, the second carbon, you will see that this carbon, 1, 2, 3. The final carbon, 1, 2, 3. So that is not valid. There is a double bond there. Therefore, each carbon will then form 4 covalent bond. So what do? We look for single bond. So I'm going to highlight this. 1, 2, 3, 4, 5, 6, 7. So there are 7 single bond there. And then for B, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 single covalent bond there. Next one, 1, 2, 3, 4, 5, 6. There are 6 single bond, because this is a double bond. And last but not least, 1, 2, 3, 4, 5, 6, 7. This is another double bond there. So there are 7 there. So which one has the most? This one has the most number of single covalent bond. B must be what we are looking for there. Question number 12. So we have this ammonium metavanadate. So we are told that there are ions. That's the most important thing. There are ions. We see that this is NH4 ions. We know the NH4 ion definitely is your ammonium cations, as stated in the paper 3 practical, as well as the paper 4 alternative to practical component. So definitely these are 1+, and because you have one lot of this NH4+, leaving behind this one must be -1, because we know that the charges must cancel each other out, as ionic compound overall has 0 overall charge. So +1, because one of these NH4+, cancel out -1 from one of the VO3-. This is quite a factual question. Question 13. They're asking for the mass of oxygen gas, which exists as these diatomic molecules O2, because oxygen being in 2,6 electronic configuration due to it being in group 6, 6 outer shell electrons want to share 2 electrons in the outer shell, therefore forming double covalent bond. If we translate that to dot and cross, you only use 2 out of 6 outer shell electrons. We don't care about the inner shell electrons because they are already full. Therefore, we are just left with 4 more electrons in the outer shell. Very commonly asked dot and cross diagram for oxygen molecule. Oxygen gas, they always refer to this 21% of oxygen in the atmosphere, in the air. And this is combined with 16 grams of sulfur to form sulfur dioxide. So we have to write equation S plus O2 giving us SO2. This is a balanced chemical equation. Now, if we have 16 grams of sulfur, we look at reacting mass. I mean, there are 2 ways of doing this, but let's just do the combined science method, which is slightly easier. Since you have 1 mole of sulfur, 1 mole of sulfur has the relative atomic mass of 32 grams, and then 1 mole of O2 has a mass of 16 times 2, because there's, diatomic molecules. We can work out SO2 there, the MR is going to be 64 because it's 32 grams of sulfur and 32 grams of oxygen, 1 mole and 1 mole, combining to give you 1 mole of SO2, which is 64 grams per mole. However, the question is really asking you if you have 16 grams of sulfur, so in reality, How many grams of sulfur do we have? We have 16 grams. We don't know how much oxygen is required. You can think of this as 32 dividing that by 2 to give you 16. So this one has to be divided by 2 as well to give you 16 grams essentially of the oxygen. So there's 16 grams of the oxygen. Is that correct? Yep, because 32 grams reacts 32 grams. So 16 grams there, you could put this as x. 32 times x equal to 16 times 32. You could get x equal to 16 grams of oxygen gas there. If you want to, you can also set up the all-in-one, which is what I normally do in all these mole calculation. So there is 1:1. On the far right, I will have the actual mole. Based on reacting masses, I want the mass of oxygen, dividing that by 32. And at the bottom, I'll have the mass of sulfur, which is 16 grams over 32. Do the math correctly, and you should be able to rearrange the equation to give you the mass of O2 as 16 grams. So they are the same answer, just based on slightly different method. Whichever method you choose, as long as you can get to the answer, no one's going to say you're wrong, correct? Now to the next question, you have this ruthenium oxide, but you don't know which oxidation number is the ruthenium. You don't know the charge of the metal, but we know that we have 5.79 grams of the oxide, and out of the oxide is just the element and the oxygen. So just ruthenium and also oxygen. So ruthenium and oxygen, this is empirical formula defined in year 9 as the simplest whole number ratio of atoms in the syllabus. So if we know we have 1.39 grams of oxygen, and both of them combined to give you 5.79 grams. So the difference there, 5.79 minus 1.39, that must give us the mass of ruthenium. So 5.79 minus 1.39, I get 4.4. That is what the calculator show you. By right should be 4.40 because these are mass. These are mass calculated based on 2 decimal place. That is as stated in the syllabus about appropriate number of significant figures, just like in practicals. So we have the mole, which is going to be the mass over the relative atomic mass, because these are about elements, about the empirical formula. From the periodic table, the relative atomic mass of ruthenium is 101. And then on the 1.39, dividing that by 16, because it's about the simplest whole number ratio of atoms, not of the molecule. So press the calculator, I get 0.044, I get 0.085. Of course, like I said from definition, simplest whole number ratio of atoms. So to get the simplest ratio, you divide by the smallest number. So if you divide by 0.044 on both sides, you're going to get 1 of this ruthenium. And then that is 0.085 by 0.044, there's roughly 2 there. So 1 ruthenium and 2 oxygen. So 1 ruthenium, 2 oxygen, that's option C there. Question 15, this question said you have an excess of solid sodium carbonate, so do not use the information on the sodium carbonate. Instead, this thing must be limiting. Limiting means it is completely used up. Used up means however much product, because carbon dioxide is your product. It's going to come from whatever that fully reacts, that's from the HCl. This is a solution. Solution chemistry must involve N equal to concentration times volume. This is the number of mole. This is concentration. Concentration is given in mole per dm cube. And therefore, this makes the volume. The volume of the solution must be in dm cube as well. We are given the volume in cm cube, so make sure you convert to dm cube by dividing by 1000 or multiplying by 10 to the minus 3. This carbon dioxide is a gas, so really we have to use the mole equal to volume of gas over 24, and this volume of gas must be in dm cube, because at the bottom of the periodic table it says dm cube, 24 dm cube for 1 mole of any gas at room temperature and pressure as stated in this particular question. I'm going to set up my all-in-one mole ratio. So I want to find carbon dioxide, so I put the mole of carbon dioxide on the top, put the HCl at the bottom because that's the information I have. I have 1 mole of CO2 from 2 mole of HCl. If you have seen my other topical tutorials, you will know that this is how I normally do my mole calculations. So what happened on top is I want the volume of gas, so the volume of CO2 dividing that by 24, that will give me the actual mole of CO2, and the actual mole of HCl will have come from N equal to C times V, 1.0 over 250 times 10 to the minus 3. Say if you don't like this times 10 to the minus 3, this is basically 250, and then press the button to the left hand side of the answer button at the bottom of the calculator, and then straight away minus 3. That's how you key this in. It has the same meaning of 250 dividing by 1000. It's just that this is a faster and easier way of notating this on your calculator. But if you can't do it, then you do it the normal way you do. And what I do is I don't change the half. I just move up all the numbers. And if I want to, I can show that dividing that by 1000. This is the same as that. That's all I'm saying. Then finally, move up the 24 to the other side. That means whatever on the left multiplied by 24. So a half times 1 times 250 exp minus 3 times 24, and I get 3, and the unit there must be in dm cube based on how we have formulated the formula earlier. Volume of gas in dm cube dividing by 24. The answer there must be D there. Question 16. This is about precipitate. So we know that barium sulfate is insoluble. Think about your test for sulfate in practical as well as alternative to practical, both of which the results will never be shown in your theory paper. Of course, these are full equations. One of the very famous questions will be write ionic equation. So there will be SO42 minus aqueous plus Ba2 plus aqueous, giving you this precipitate of BaSO4 aqueous, which came from one of these and one of that. This is a classic precipitation reaction. You are forming something insoluble, which you can filter off, and you can wash it with distilled water to get rid of all this aqueous stuff, and then you can just dry it to get pure sample of the barium sulfate. So you do filter it off, wash and dry and weigh. You get 5.36 grams of barium sulfate. This is the actual yield. The question is, to find out the percentage yield, you need to find theoretical yield. Find 100% yield, which is the theoretical yield, from the balance equation. So the mole of barium sulfate is what you want to find, because you want to find the mass of barium sulfate. What information do I have? I use excess of barium chloride, so this thing must be limiting. So I'm going to use this N equal to C times V, because this is concentration, this is volume. So that is the mole of the sodium sulfate. And they happen to be 1:1, which means they are equal there. So what I can say is going to be, if I have on the top, what do I have? I want the mass of barium sulfate. So the mass of barium sulfate, dividing that by the MR of barium sulfate, which is already given in the question very, very generously. At the bottom, I'll have N equal to C times V, because I have solution. So 1.00 mole per dm cube times 25.0 times 10 to the minus 3. Again, if you don't like this times 10 to the minus 3, as a pure science student, you should really be worried if you don't like it. But if you really don't like it, you can do 1.00 times 25 over 1000. What you're going to do then is just rearrange the equation, move up the denominator to the other side. 1.00 times 25.0 times 10 to the minus 3. That is the mass that you want, and that is dividing that by 233. I'm just going to show you that the 233 can be moved up to the other side, and then that become multiplied by 233, and therefore overall you just need to key in your calculator for the final answer. 233 times 1.00 times 25.0 exp minus 3, I get 5.825 gram. Remember, these are mass balance that can measure 2 decimal place, so by right it should have been 5.83 gram to 2 decimal place. However, they want the percentage yield, so that means this is how much you actually get out of the total. How much you actually get is actually 5.36 gram. So out of the total 5.83, you are only getting 5.36 gram. So get that as a percentage, and what I get then is I get 91.9%. 91.9%. To the nearest whole number, there's 92% there. Question number 17, we have aqueous copper to sulfate. So this is a pale blue solution containing your Cu2 plus, your SO42 minus. But then we have an aqueous component which gives us the H plus as well as the OH minus component as well. So in terms of the inert electrodes, such as platinum or graphite, what about this electrolysis is going to be correct? So among the ions, since we are not using copper electrode, we are not going to transfer copper from anode to cathode, because that is what happens if you use copper as the cathode and anode. But in terms of inert electrode, you're going to, instead of the Cu2 plus, well, between the H plus and the Cu2 plus, is actually going to be the Cu2 plus that's going to be discharged at the cathode, simply because copper is below hydrogen in the reactivity series. It started with posocarmazole, so that is the potassium, sodium, calcium, magnesium, and then aluminium. And then the zale is zinc, iron, and lead. And then beyond that, you have hydrogen. And directly below hydrogen, you have copper, silver, and gold. We also know that carbon lies somewhere in between aluminium and zinc. Having said that, copper is below hydrogen in the reactivity series. You're going to prefer to discharge copper at the cathode. Cations go to cathode. We know that cations go to cathode. Red cat there refers to reduction happen at cathode. And we also know about the oil rig acronym. So in terms of the oil rig, we know that the rig, RIG, that is reduction, is gain of electrons. So your cations are going to go to the cathode, and then your cations are going to gain electrons at the cathode as reduction happens at the cathode. So in terms of the collection of copper, we're going to have Cu2 plus 2 electrons going to copper. This will be reduction at cathode there. So for the first option, copper is not collected at the anode, copper is collected at the cathode, so A is definitely wrong. You don't get hydrogen, you get copper because copper is below hydrogen in the reactivity series. The further down you are, the more you favor reduction. Oxygen is collected at the anode. Between the sulfur and the hydroxide is going to be preferred to be discharged, as you don't have any halide and you don't have any concentrated solution here. Writing half equation is a very important exercise for this electrolysis topic. So we know that it forms oxygen. Water is not a product. Water is simply already present in the aqueous solution. So it's not a redox product. It's just something which is needed to balance the equation. Balance the atom first. We need 2 of that, and we need 4 of that. Having done that, we have -1, 4 of them, giving us -4. So we do need 4 electrons there. That is oxidation at your anode, as that is the hydroxide ions losing your electrons there. Your hydroxide ions losing your electrons. This is part of the acronym. Oxidation involved, or oxidation is the loss of electrons, whereas reduction is your gain of electrons, and that happens at the cathode. So this oxidation happens at the anode. We do get oxygen, we do get it at the anode. C must be the answer. We don't collect sulfur, so not the SO42-, but the OH- that get discharged there. Question number 18, this is about concentrated solution containing your halide, your group 17 ions, not group 17, you call it group 7 in O-level or IGCSE chemistry actually. So there's group 7 halide ions. So what we have is Na plus Cl minus. We also have the aqueous component H plus and OH minus. Typically speaking, if we have aqueous solution, we would favor the hydroxide, which will give us oxygen gas at the anode, just like the previous half equation shown above for the previous questions. However, because we have concentrated solution here, we're going to favor the halide over the hydroxide being discharged. In terms of hydrogen and sodium, despite the concentrated solution, hydrogen is still all the way further down in the reactivity series compared to sodium. Where there is a choice, you will always go to discharge to reduce the less reactive species, in this case the hydrogen at the cathode. So cations will go to the cathode, and then we know that red cat means reduction happened at the cathode, so they will gain electrons because reduction involve gaining electrons. So that will go to hydrogen gas. Balance your atom with 2 hydrogen atoms, and then balance your charges with 2 electrons, so that the +1 times 2 is +2, cancel out -1 times 2 -2. Altogether on the left is 0 charge. Hydrogen molecule doesn't have any charge. This is reduction happening at the cathode. You want at the anode, you don't want at the cathode. So we know what also happened at the anode. It will be the Cl- they go to Cl2. Because this is reduction at the cathode, there's gaining of electrons, where you gain electrons on the left hand side. So the other side must involve the loss of electrons. We're going to balance the atom with 2 Cl-, and then going to balance the charges with 2 electrons there. So that's just your oxidation at your anode. Your anion is negatively charged species. Your negatively charged ions go to the anode, where they lose electrons. Oxidation involves loss of electron. So we can say Cl- loses electron, Cl- get oxidized, where oxidation involves loss of electron there. So at the anode there will not be the H plus, will not be the O2 because it will not be the hydroxide that get discharged. The Cl minus gaining electron will give you more negative charge, doesn't give you zero. Gotta know how to balance atom as well as balance charges there. Question 19, this is again about electrolysis. Seems like 3 questions on electrolysis in a row. This is molten. Molten is a pure substance. There is no water. There is no water. It is not aqueous component. So we got Ag plus, which is the cations. So cations are positively charged ions. Cations will go to the cathode, and cathode is where reduction happens. Reductions involve gaining of electrons. So your cations will gain electrons at the cathode, and you will get this particular silver metal being discharged. So at the cathode, it's not Ag2 plus, silver 1 cations, as you would have known with all the formula involving silver chloride, AgCl, silver bromide, HBr, silver iodide, AgI. They are all in the test for halide ion from paper 3 as well as paper 4, which of course they do ask you in the theory as well, such as this. So we also know red cat, and the cations will go to cathode. Cations are positively charged ions, and this makes the cathode oppositely charged terminal, which is negative terminal. So negative ion and ion doesn't go to cathode there. Having done that, A and D are definitely out already. We can then think about at the anode. At the anode, we know that's where oxidation happens. This is a pure species, molten electrolyte. It's going to give us this halogen by losing electrons, by losing 2 electrons, as there are 2 bromines. So 2 of that, 2 times -1 is -2. Each electron is -1, you need 2 of them. So really we're looking at that because again, this is a group 7. This is a group 7 halide ion. Your group 7 already have 7 outer shell electrons, and therefore when they form ions, they just need to gain 1 extra electrons in order to complete the outer shell. Cannot be 2 minus there, just -1. So answer there must be option C there. 20, which 2 processes are both endothermic? We know that endothermic is represented by enthalpy change being greater than 0. That is because your reaction will have absorbed heat energy. So you absorb heat and you absorb it from surroundings. Having done that, this means that your surroundings will get colder. The temperature of the surrounding would have decreased there. So which 2 processes are endothermic? Well, combustion is definitely exothermic, so anything with combustion is going to be out of the question. When we see enthalpy change of combustion, that is always going to be lesser than 0 exothermic. When you burn something, it releases heat to the surrounding there. So we just have to choose. I mean, photosynthesis is already there. So respiration is the opposite of photosynthesis, as these are in opposite directions. We know that respiration is basically burning calories, C6H12O6 plus oxygen gas. You're burning the food in the body by breathing the oxygen, and you're doing respiration. So that essentially is the combustion of food in the body, going to give you CO2 and H2O. That's our respiration. Equation must be balanced with the 6 carbons and then 12 hydrogen, so there's 6 water. You can balance the oxygen. 6 oxygen balances the 6 oxygen on the right hand side, but we've got 12 oxygens there from the 6 CO2. We need another 6 O2 there. So this is essentially burning calories. This is essentially combustion of food inside your body. This is going to be exothermic reaction, so not an endothermic reaction. And actually that makes photosynthesis endothermic, because photosynthesis is the opposite of respiration, where it's the same equation but in the opposite direction. If you draw an energy profile diagram, you would know exactly what I'm talking about there. Cracking is just shortening long chain carbon by breaking up covalent bond. So obviously you do need energy. You do need high temperature, like very high temperature of around 500 degrees Celsius, and that is in the presence of a catalyst already. Imagine without a catalyst, the temperature required would be even so much higher. So catalyst is required there to help you reduce the energy demands and make the reaction go at an appreciable rate under a less extreme condition there. Question 21. So we have 10 grams of zinc granules. We have sulfuric acid. So that's the metal plus acid reaction. Zinc plus sulfuric acid. Not sure if we need this equation, but give us zinc sulfate. Both ions are from practical. Zinc 2 plus ion, SO4 2 minus sulfate ions. Metal plus acid gives us metal salt and also hydrogen gas. So the rate of this reaction increase if I add a small amount of copper. The copper is unchanged after the reaction. This suggests that the copper is a catalyst, because catalyst is a substance that increases the rate of reaction without itself being chemically changed, without itself being used up. You still have the exact same amount at the end. How does it act as a catalyst? It offers you an alternative reaction pathway, which you should be able to draw an energy profile diagram showing the activation energy in the presence of a catalyst versus without catalyst. So there's your progress of reactions or extent of reaction going from the left to the right hand side. So in your enthalpy change diagram, so enthalpy change is from your reactant to your product, and then we will know that enthalpy change is the energy difference going from the reactant to the product. So it's going one direction, it's coming down as exothermic. I really don't know if this reaction is exothermic or endothermic by theory, but by experimental skills and by practice, I've done this in the lab, I know it is definitely exothermic. That's not the question here. The question here really is the activation energy. The one in red there, this is without catalyst. And how would this be different if you had used a catalyst? You're going to have an alternative reaction pathway. Overall, it's going to have a much lower activation energy. So the one in black now, the activation energy is a new lower activation energy, and therefore there will be more molecules that can overcome this lower activation energy, and therefore this can increase the rate of reaction. So in terms of biological catalysts, that is not true, because biological catalysts will have been something like enzymes, and we're talking about transition metal. Transition metal is not a biological catalyst, and therefore it's not acting as a biological catalyst. It is acting as a catalyst, and therefore it does give you this alternative reaction pathway with a new and lower activation energy. So B must be our best answer there, considering the copper is catalytic, and therefore you need a small amount, and itself doesn't get changed or doesn't get reacted by the end of the reaction. So the rate of the reaction is greater as the particle size is greater. It becomes smaller because as it reacts, it will get smaller and smaller. The rate of reaction is greater, pressure is increased. It's irrelevant because your reactants are not gases. So even if you increase your pressure, it's not going to affect the sulfuric acid, which is a solution aqueous, as well as your zinc granule, which is a solid and not gases there. So C and D are not going to be much relevant. Question 22, we have rate of reaction between magnesium and dilute hydrochloric acid. So this is again metal plus acid giving you metal salt. We have a Mg2 plus group 2 ions, Cl minus group 7 ion. Looking at the valency, which is the charges, the value of the charges. And then we do lowest common multiple, primary school mathematics, to get the lowest common multiple. In this case, we must have one of the Mg2 plus and two of the Cl minus, such that we get MgCl2 as the formulation for magnesium chloride. You know that solubility of chlorides, all chlorides are soluble except for silver chloride. AgCl will be a solid, and also lead-2 chloride, lead-2 plus Cl minus, Pb2 plus Cl minus, you get PbCl2, not aqueous but as a solid. Both of them are classic white precipitate in your experimental chemistry. This metal plus acid give you metal salt and hydrogen. We have an excess of acid, so that means all of magnesium is used up, because all of magnesium is your limiting reactant. Limiting reactant means all of them get used up. So the concentration of HCl and the volume of hydrogen produced is measured at regular time intervals. So in terms of the concentration of HCl, because there's excess of it, you are not going to be used up all of it, because in the question it said excess HCl. So why would you be using up all of it at the end of reaction? So A and B cannot be the answer there. So here we can see that HCl is in excess, so that means it is not used up. So sometimes you do need to keep an eye out for this kind of thing in the question. So in terms of the volume of hydrogen, it does come to a stop because, once the limiting reactant is used up, in this case, in this particular case, the HCl is in excess, the Mg is used up. That means reaction stops because there is no more magnesium. So this one implies that, it's not being used up, but we know that it will slow down such that your gradient becomes 0 because it becomes horizontal lined. horizontal line doesn't have a gradient. The gradient is 0 because there is no change in the vertical axis. So horizontal line there, gradient 0 there suggests that the reaction will have stopped, and that is where the reactant, the limiting reactant, will have been used up. So D must have been the best answer of all. Question 23, we're looking at reduction. Reduction has quite a few meanings in the definition in the syllabus. It involves the loss of oxygen. This is in fact one of the most useless definition of all. Most of the time we are looking at the gaining or the losing of electrons. We know in terms of oil rig acronym, the RIG there stands for the reduction, which is gain of electrons. You are gaining negative charge electron. Be very careful there. Last but not least, we think about the oxidation number, or the oxidation state will decrease in that particular reaction. So look at the first one. The underlying species is calcium. In calcium carbonate, we have Ca2 plus and CO3 2 minus. So for the Ca2 plus, we look at the charge of the ion, so that's calcium plus 2. Then we have calcium chloride, which is essentially a salt, so Ca2 plus, Cl minus. Again, we have Ca2 plus, so that's calcium plus 2. There is no change in oxidation number. The first one is definitely not redox in terms of the calcium. For the calcium, it's definitely not redox. Okay. Second one, copper plus 2, because you have copper 2 plus, and then you have copper metal. This is metal, this is element. It has got no charge. It's not an ion. This is copper 0. Plus 2 becoming copper 0. There's a decrease in oxidation number, and therefore this must be reduction of the copper. Having done that, we know the other two are definitely wrong. So what do we know in this case study? The CO is used as a reducing agent because the CO itself gets oxidized. The CO gain oxygen. So the easiest one to see is the CO gains oxygen atoms, because just now it has one oxygen atom, and now you have two when you form CO2. Gaining of oxygen atom is going to be what you call oxidation, not reduction, but the CO itself get oxidized. Therefore the CO is acting as a reducing agent. So it is a reducing agent as it reduces the iron trioxide to become iron. This is iron trioxide, not iron 2, because essentially what you have there is iron 3 plus, and you got 3 of the O2 minus, lowest common multiple. The charges must cancel out, and therefore you get 2 of the iron 3 plus and 3 of the O2 minus. Last but not least, we also know that the last one is definitely wrong. Zinc as a metal, this is zinc as a salt, so it's zinc 2 plus, therefore there's zinc plus 2. Increase in oxidation number is oxidation for the underlying species there. Question 24. Again, we're looking for reduction. Ooh, a lot of repeated ideas really. So in part A, we have decomposition of the group 2 carbonate. This is called thermal decomposition as part of metal chemistry. Group 2 carbonate can decompose to give you group 2 oxide and CO2. So looking at this, we can see the calcium 2 plus remain calcium 2 plus. So really there is not much change there. This is a CO3 2 minus therefore. Or if you want, you can think about 0 being overall oxidation number of a compound which is uncharged. The calcium is going to be plus 2 as a group 2 metal in a compound. Carbon is what you want to find. 3 times oxygen. Each oxygen has a minus 2 in a compound. The carbon there is plus 4. Having done that, calcium oxide is the easier one. Calcium 2 plus, there's calcium plus 2, no change. Oxygen minus 2, no change from the carbonate. I'll just work out for the carbon dioxide, 0 for the overall molecule. The overall compound doesn't have any charge. 2 times minus 2 for each of the oxygen is minus 2 in a compound when they are bonded to something else. You could see that it's carbon plus 4 and carbon plus 4. You are looking for reduction. You're looking for one part of redox. A is not a redox. This is just thermal decomposition of group 2 carbonate to this oxide. Copper to brass. Brass is a mixture. So it's an alloy. It's a mixture of metal. If I'm not mistaken, brass is actually copper and zinc. Okay, but I could be mistaken. I know it's an alloy, ALLOY, and it's got like different metal cations of different sizes. Definitely not redox because it is still the metal itself. Ethene to polyethene is what you call addition polymerization. Addition polymerization is part of alkene chemistry in organic chemistry, definitely not reduction there. In terms of sand, sand is going to be SiO2, silicon 4 oxide, silicon dioxide going to silicon. We can see that just now you have oxygen, now you no longer have oxygen. So the SiO2 loses oxygen to form silicon. Loss of oxygen is reduction, and it was mentioned in one of the 3 definitions of reductions in the syllabus, in the curriculum. Question 25, we have thiosulfate ions. So we're looking for definition of oxidation and reduction again. So the oil rig acronym. So oxidation is your loss of electrons, whereas reduction is your gain of electron. We gain electron on the left, we lose electron by adding the electrons on the right hand side. So what do we see here? We see the S2O3 2 minus. So that's what I'm going to do. Just focus on the S2O3 2 minus. Going to S4O6 2 minus. You can see that 2 times 2 is 4, 3 times 2 is 6. So what I'm going to do is put the 2 in front. What I'm going to do now is balance the charges. Minus 2 times 2 is minus 4 on the left. Minus 2 times 1 is minus 2 on the right. I'm missing a minus 2 on the right hand side. And I can say that, having said that, I can see that I have added 2 electrons on the right hand side. It means from the left to the right, what actually happened? The S2O3 2 minus loses electrons. So therefore, the S2O3 2 minus gets oxidized. So that's your oxidation there. And that is your S2O3 2 minus get oxidized because you lose electrons there. So C must be the answer, not A and B there. Question 26, we're looking at contact process. It's one of the 4 steps in the contact process. The first one involves sulfur plus oxygen, roasting the sulfur and oxygen to give you SO2. Of course, the second step is as shown above, where you have the reversible step, and you have to have specific conditions in order to favor the equilibrium to the right hand side to maximize the yield of SO3, but also get it at a good enough of a rate. The third step in industry involves you not adding water straight away. Instead, you are going to get oleum by dissolving SO3 in corn sulfuric acid, add up all the atoms, you get H2 and then 2 sulfur, 1 plus 1, 4 plus 3 is 7, so there's oleum there. And what you do with oleum is you just add water to the oleum, but not directly to the SO3, and you get H2SO4 to balance the equation 2 of it. So these are man-made process. Well, in fact, the whole process are man-made, and it's different from the acid rain formation, which is H2SO4 being formed in the upper atmosphere, giving you H2SO4 and the rainwater. You don't have the equilibrium step. In fact, you don't use inorganic man-made catalyst. You would use things like nitrogen dioxide as your catalyst up there. That is natural atmospheric oxidation of your SO2 to SO3. This is man-made contact process. Anyway, so what do we have? Adding more oxygen. Now we know about this idea of equilibrium will oppose the change. So when you add more oxygen, equilibrium tries to react more oxygen because you want to decrease the oxygen. Therefore, you react more oxygen. When you react more oxygen, you're going to favor to the right-hand side. You want to favor to the left. When you react more oxygen, you're going to favor more to the right-hand side. So A cannot be the answer. In terms of pressure, pressure affects gases. We can see that 2 plus 1 give you 3 moles of gases, and these are on the left, and then you have 2 moles of gases on the right. Whenever we're dealing with pressure, we're thinking about gases. We don't count the solid or the liquid because pressure affects gases the most. So 3 moles of gas on the right, on the left, versus 2 moles of gas on the right. When you increase pressure, what will equilibrium tries to do? Equilibrium tries to lower the pressure, tries to decrease the pressure. Of course, you will shift the equilibrium to the side with lesser gases. So you will shift to the right again, so B is not correct. In terms of C, we can see that the forward reaction, they don't tell you it's forward, but if they give you equilibrium and they show you the enthalpy change, and this is negative, so we can say that the forward reaction is exothermic. If the forward reaction is exothermic, it releases heat energy to the surroundings. When temperature increases, what would your equilibrium tries to do? It will try to decrease your temperature. But how do you do this? You only know how to release energy. You will only release less heat because you want to help the surrounding to be a bit cooler, as that is what you try to do to oppose the change, as I have written before. Decrease temperature of the surrounding, therefore I will release less heat. Going forward from left to right, I will release heat energy. If I release less heat, I'll favor more to the left hand side, I'll favor backward reaction. So C must be what we're looking for, which means D must be wrong. Now, when you remove SO3, what would the equilibrium tries to do? Equilibrium will tries to make more SO3 because you want to increase the concentration and therefore have more SO3 in the equilibrium. So you just make more SO3 and therefore they will favor to the right hand side again. Not really what you want there. Question 27, we have this magnesium salt of a fatty acid. So what is the carboxylic acid functional group? I can see that this is alcohol, so we don't have that carboxylic acid C double bond or OH fully displayed, and we know that this is the acidic protons. That is the acidic proton because you know how to write the partial dissociation. Partial dissociation is written with the equilibrium sign, reversible sign. Weak acid partially dissociate the solution to give you H+. Now, how many moles of a fatty acid react with 1 mole of magnesium? This is a tricky question. Magnesium is a group 2 metal, and I should have used the Roman numeral actually. I was a bit confused between A level and O level. Now this is 282. How do you get to a completely filled outer shell? You will get an Mg2 plus ion. Having done that, we can see that you only have one carboxylic acid group. So that means you're going to have RCO2 minus, which is the same as RCOO minus, which is basically that carboxylate. Anything carboxylate ion, we have come from the carboxylic acid. It's got the OH in the name, such as metanoate, ethanoate, propanoate, and so on and so forth. Both of them are the same. We know that when we balance equation, we are looking at the charges. Well, when I say balance equation, I mean balance formula. So 2 and 1 are what you call the valency, which are based on the charges of the ion. The objective is quite simple. Balance the charges. So all we're going to do is LCM. Cross multiply the valency so that you will get the lowest common multiple. How many is the level? It means you need 1 of the Mg2 plus and 2 of that carboxylate. So 1 of the Mg2 plus and that RCO2 minus, you need 2 of it, since your carboxylic acid only contains 1 carboxylic acid, giving you that -1 charge there. So the functional group has to be got A or B for the fatty acid, for the carboxylic acid. And because if you have 1 mole of magnesium, 1 magnesium needs 2 of the acid to react. So the answer there must be B there. Question 28, we have salt. So these are 2 different salts because the H plus of the acid, in this case the sulfuric acid, and also sulfuric acid can dissociate 2 times, giving away 1 H plus, you're going to get HSO4 minus. And then you give away another H plus, you're going to end up with SO4 2 minus. Now they both can be prepared from this reaction of sodium hydroxide and sulfuric acid. It just depends on the mole ratio. If you have 1:1, then you're just going to take away 1 H plus, and therefore you form 1 water. If you have 2 moles of NaOH is to 1 mole of sulfuric acid, 2 of the OH minus can take 2 of the H plus to give you 2 moles of water, and therefore giving you the sulfate salt. Now in each reaction, we use 50 CNQ or 1 mole per DNQ sodium hydroxide. This is concentration in mole per DNQ. This is the volume of solution, not a gas. So this is the classic N equal to CV to calculate the mole of solution. That is your concentration. It must be in mole per DNQ. Having said that, it means that your volume must be in DMQ as well. So CMQ must be converted to DNQ by dividing by 1000. So now you have 1 mole per DNQ sulfuric acid. Looking at the mole ratio, be careful about mole ratio and volume ratio. This is sodium sulfate. So this is reaction 1. And then we have reaction 2 in the second bit there. I think it will be easier to do reaction 2 first because it's 1 mole is to 1 mole there. Am I correct? Okay, so the hydrogen sulfate there is your reaction 2 there. So this is sodium hydrogen sulfate there. And if we have the same concentration, so we can see that in reaction 2, we have the mole of NaOH is equal to the mole of H2SO4 because of 1:1 ratio there from the balance equation. Now what do we have? We have the NaOH information, 1 mole per dm cube, 50 over 1000 cm cube changed to dm cube there. I have the concentration of the acid, the sulfuric acid, which is 1 mole per dm cube. I just need to know the volume of the sulfuric acid required, and this is in cm cube, and therefore I divide that by 1000 by comparing the 1 and the 1, and then the 1000 and 1000 at the bottom. You should be able to do the math and get the comparison correct, or you can do it manually to do the calculation on a calculator. I would definitely need 50 cm cube. Having done that, my decision will have gotten me option A, because that's the only one that gave me 50 cm cube there. Now, can I prove the other one? Can I prove the value? Of course I can. It's just mathematics. If I see reaction 1, so what I have is the mole of sulfuric acid is to the mole of the NaOH is going to be 1 mole of sulfuric acid is to 2 mole of the NaOH. This is my all-in-one method. So what I'm going to do is, let me see, I think I'm running out of space there. I'm just going to move some stuff around and see if I can fit everything on this side. Should be able to. So this is for reaction number 1, yeah? And then I have N equal to C times V, because that's the actual amount of mole for the sulfuric acid. So I need the concentration, which is 1 mole per dm cube. I need the volume over 1000 for the volume of H2SO4 in cm cube, dividing that by 1000. And at the bottom, I have 1 mole per dm cube of the sodium hydroxide and 50 cm cube of the NaOH. Now, if you can see, the 1000 and 1000 can cancel. If you can do the math correctly, denominator at the bottom move to the top there. That is half times 1 times 50. Your volume is going to be half of 50 cm cube, which is actually 25 cm cube. Having done that, I should be able to, get that A is the answer. But of course, when you're going through the options, you should have been able to check with N equal to CV and get the 1:2 ratio for the first one, and then 1:1 ratio in terms of the volume multiplying by concentration to give you 1:1 for the second reaction there. Question 29, we are looking at what substance will react with dilute sulfuric acid. So we got to think about reaction with acid that can react with metal to give you metal salt and hydrogen, that can react with metal carbonate to give you metal salt, carbon dioxide, and also water. That can also react with a base, which is typically metal oxide, metal hydroxide, or you could have, well, actually some metal hydroxide is soluble, which would turn out to be an alkali if it is soluble in water. You just want a pure sample of lead to sulfate. What do we know about solubility of sulfate as stated in the salt preparation syllabus? So all sulfate are soluble except for 3 particular sulfate. The first one is your typical test for sulfate. That is your barium sulfate, white precipitate. We also have the second one, which is insoluble. There will be the calcium sulfate. And the third one is your lead 2 sulfate. So the fact that we have lead 2 sulfate here, this is insoluble. This is insoluble. So if we are preparing something insoluble, this is the idea of precipitation. Precipitation reactions come from mixing 2 aqueous solutions together. So we're going to have aqueous and aqueous coming together to precipitate out your insoluble precipitate, which can be filtered, washed, and then dried. So not going to be the metal, not going to be the powder, which are solid. So B, C, and D are going to be solid there. So B, C, and D are not going to be suitable. This is nitrate. All nitrates are soluble. You use a solution of these together with a solution of acid. It's going to precipitate out the lead 2 sulfate. We're going to write an ionic equation for this precipitation reaction. This is Pb2 plus combining with SO4 minus, giving you a precipitate. One of the Pb2 plus aqueous solution, SO4 minus from the acid aqueous solution, aqueous and aqueous giving you the solid insoluble precipitate. One of these, one of that. The charges cancel out, no charge for the ionic compound there. Very popular to write ionic equation together with the correct stat symbols based on the solubility rules. That was part of salt preparation from year 9, which will be covered again in year 10, acid, base, and salt topic. Question 30, this is about the sulfuric acid statement as part of the contact process, of course. Now in the contact process, we don't use iron, we use vanadium 5 oxide. The 5 there is in the Roman numeral. Candidates should know how to name compounds, especially that of transition metals, using the Roman numeral for the correct oxidation number. There's V2O5, vanadium plus 5, O2 minus, 5 and 2, 2 and 5. This is basically your valency, your combining power. At the bottom is how many of these do you need to combine together. 2 of the vanadium 5 plus, 5 of the O2 minus. So A is definitely wrong there. Sulfuric acid is used in batteries. That is true, especially for car batteries. And that means the other two must be wrong. We don't use sulfuric acid as a fertilizer. We can react sulfuric acids such as ammonia plus sulfuric acid. NH3 plus sulfuric acid can give you ammonium sulfate, NH4 twice SO4. You have NH4 plus, and that's going to replace the H plus in the acid. When you replace the H plus in the acid, you are going to get, salt. So you do need 2 of these ammonium cations, and you do need 1 of that sulfate anions in order to balance out the charges. Plus 1, plus 1, plus 2. Minus 2 times 1 is minus 2. Your charges cancel, and we got to balance the equation. 2 ammonium comes from 2 ammonia, and 1 sulfate comes from that. You don't need to produce water, especially when ammonia acts as a base. Together with acids, you just form ammonium salt without needing water to balance the equation. Sulfuric acid is not used as a food preservative. Actually, you will use sulfur dioxide, which is SO2. SO2 is very well known as an antioxidant. If you have ever bought, dried fruits, they will have in the ingredient with permitted sulfur dioxide as antioxidant, all as food preservative there. Question 31, we have 2 statements. This is about periodic table chemistry. This is about group 1 and group 7. We know that group 1, we are talking about metals. And we know that in terms of the metals, lithium, sodium, potassium, your size of the cation is getting bigger and bigger. So we talk about the giant metallic structure where you have the layers of cations. And then what we have is we have delocalized outer shell electrons. But if your cations are getting bigger and bigger, even though they have a +1 charge for all the group 1 metals, but your cations are getting bigger and bigger going down group 1, therefore the charge divided by the size, the charge is the same, the size is getting bigger, the net charge density of the cation is getting smaller, getting less attracted to the electrons, weaker metallic bonds. Gotta think about what is metallic bond to begin with. And if you have weaker metallic bond, your melting point is going to go down. So melting point increases is not true. So 1 is definitely not true because they're looking for correct statement. 1 is definitely not true. A and B are out already. When you look at group 7, we got to know about a few things. Fluorine, chlorine, bromine, iodine. In terms of their stat symbols, fluorine and chlorine, they are gases at room temperature and pressure. Fluorine is borderline colorless. Chlorine is a pale green gas as stated in the syllabus. Bromine is a reddish brown liquid, whereas iodine is a gray-black solid. And having said that, we can see that the melting point, their boiling point, increases down group 7. And that is because these are simple covalent molecules. You have got stronger intermolecular forces going down the group 7. These are forces of attraction between the molecules. If you require more energy to break them, they're gonna have higher boiling point, higher melting point as a result. So the melting point increases there is true for group 7. But we already know statement 1 is wrong. I should have, gone straight to statement number 2, which of course, based on their oxidizing and reducing ability, we are talking about the halogens. They become less likely to gain electrons because you have more filled electron shells. So what happened there is your electron to be added is further away from the nucleus. If that electron that you are adding is further away from the nucleus, is going to be less attracted, therefore less attracted to the nucleus. If you are less attracted to the nucleus, you're going to become less favored to gain electrons. If you become less favored to gain electrons, you become less likely to be reduced itself get reduced because they are oxidizing agent, but it becomes weaker and weaker oxidizing agent. In terms of reactivity for the displacement, we know that fluorine can displace chlorine from chloride, and chlorine can displace bromine from bromide. Bromine can displace iodine from iodide, but not the other way around. Chlorine can displace iodine from iodide. That first statement is correct. Chlorine cannot displace bromine from potassium bromide. That second statement is wrong because it says chlorine cannot. Chlorine can, because chlorine, Cl2, is a stronger oxidizing agent than Br2. Or you can say chlorine Cl2 is more reactive than Br2, even though we are reacting with Br minus. But we talk about the reactivity between the halogens molecules. Cl2 is more reactive than Br2. Therefore, Cl2 can kick out Br2 from Br minus. So which one is correct? Statement 2 is correct. Oh, hang on. Statement 2 is wrong because it said cannot. So statement 2 is actually also wrong. And therefore, statement 2 being correct is definitely wrong. So neither statement 1 nor statement 2 is correct there because none of them are correct there. So be very careful about reading the trend and coming to the final option. Question number 32, we have reversible reactions. A solid reacting with hydrogen. A solid reacting with hydrogen. Which one would catalyze the reaction? So these are metals. This is a group 3 metals, whereas iron is a transition metal. Having seen the questions, you should see that there is this word called catalyze the reaction. It will make the reaction go faster. It has just to be the transition metals, not the aluminium. Therefore, I will have chosen A and B there. And then what is the effect of catalyst on the equilibrium position? It will be no change because catalyst only increases rate. It only affects how fast a reaction proceeds. It doesn't react, doesn't affect how much. It doesn't affect how much, which is your equilibrium yield, your equilibrium position. That one is not affected by catalyst, as catalyst only affects how fast, which is rate of reaction. Question 33, we have the extraction of iron in the blast furnace. We know that there are quite a lot of steps. The first of which is the carbon. So that's why you need the carbon charcoal or the coke. So this is your coke there, reacting with oxygen to give you carbon dioxide. And then your carbon can react with more carbon dioxide in a redox reaction to give you carbon monoxide. And then your carbon monoxide is the key ingredient as your reducing agent. Itself will get oxidized by taking away the oxygen from the Fe2O3 iron 3 oxide. This is your hematite ore from the ground. The thing is, you have 3 oxygen to be given away, and each CO can gain 1 oxygen. So altogether, you do need 3 CO to take away 3 oxygen, and then you would also form 2 iron there. That's your balance equation. In the 4th step, we do need another raw materials in the extraction of iron. This is your limestone, which can undergo thermal decomposition in the presence of high heat in the blast furnace. You get this basic oxide, because this is not in solution. This is just a solid oxide. Last but not least, you have silicon dioxide, which is acidic oxide. Can react with CaO. This is at very, very, very high temperature. You get calcium silicate. This is what you call slag. This is to remove the acidic oxide. This is acid and base neutralization reaction, as the acidic oxide react with the basic oxide, and they give you this calcium silicate, CaSiO3. Should have known about carbonate, so CO3 minus. Silicon is just below carbon, so this is called a silicate anion. It's going to have the same charge as the carbonate ion. The silicon is just below carbon. Calcium carbonate is used to remove acidic impurities. You can't, but then the calcium carbonate doesn't react directly with the acidic impurities. Instead, what we can say is calcium carbonate forms the calcium oxide first, only then reacts with the acidic oxide there. I think A can be accepted, but let me just go through the other option as they are looking for correct statement. They say the carbon coke is reduced to carbon dioxide. The carbon coke gains oxygen. So if you can see here, the carbon gains oxygen, the carbon gets oxidized. So that is your oxidation there, gaining of oxygen. So that is not reduced, that is oxidized. So B is definitely wrong. Hematite is oxidized? Not really. Hematite loses the oxygen. So we can see the Fe2O3 loses your oxygen. Loss of oxygen is your reduction. So that is reduced by carbon monoxide there. Hematite undergo thermal decomposition? That is not true. There will be a limestone. Limestone is your calcium carbonate that undergo thermal decomposition. So again, it doesn't really react directly with the SiO2, but you can think about it. It does perhaps, but usually it proceeds via this thermal decomposition first. Then the calcium oxide can neutralize the SiO2 there. Question 34, we have carbon cycle. The main important thing in carbon cycle is net carbon neutral, or net carbon being 0. That means whatever amount of carbon dioxide given out by human activities such as combustion, which does require oxygen, and then it will release carbon dioxide. And also respiration. Respiration also release carbon dioxide. Then we need photosynthesis in order to react with the oxygen, and that is done by the plants in order to remove the carbon dioxide. Having said that, that is going to exist in the perpetual cycle. And of course, if you have more and more human activities and you cut down more and more trees and therefore less photosynthesis, then we are not going to achieve net carbon 0, and therefore that is not going to keep the carbon cycle very happy then. So the carbon cycle regulates or controls the amount of carbon dioxide in the atmosphere. We're looking for correct statement. 1 is definitely correct there. During photosynthesis, you don't produce carbon dioxide. Carbon dioxide is reacted. Instead, what is produced will be oxygen gas. That is what is needed. 2 is definitely wrong. 2 is definitely wrong. 2 is definitely wrong. So 1 is definitely correct. 1 is definitely correct. And what are we looking for? So that means B must be the only answer because 2 is definitely wrong there. And 1 and 3 is correct because combustion, burning hydrocarbons, compound containing hydrogen and carbon, definitely require oxygen to produce carbon dioxide and water if it is complete combustion. Carbon is used in the purifying water supply. So we know that this is a very direct question, just to remove taste and odor, because carbon is actually used in water filter for this exact same function. We know to sterilize the water, that would be the chlorination step. So in the chlorination step, we would pass it, or we will add aqueous chlorine, and they will kill microorganisms and harmful bacteria. First one, to remove insoluble solid, there will be your filtration stage. As for this removing nitrates, that's going to be tricky because all nitrates are soluble. That is why this last step is going to be, sorry, not the last step. These removing nitrates are going to be extremely tricky, and that is why too much nitrate being used in fertilizer is definitely going to cause excessive growth of algae or algae on top of the river water. Eventually, as stated in the syllabus, this is going to lead to deoxygenation of the water, and therefore all the aquatic plants and animals will die as a result. Question 36, this is organic chemistry question. Octane is an alkane with 8 carbon atoms. So this is 8 carbons, and then is an alkane. So we're looking at the general formula first of all, CnH2n plus 2. So looking at 8 carbons, so we're going to work out 2n plus 2. That is 2 times 8 for 8 carbons. Add with 2, we're going to get 18. So 16 there is going to be wrong because there will be CnH2n, which is for alkene, not for alkane. So A and B are out. In terms of the boiling point, comparing that with butane, we know that in the fractional distillation of crude oil, the heavier you are, the further down you are in the fractionating column. We have fractional distillation, therefore we have fractionating column. So at the very top, or closer to the top, is your light fractions. It will be your low boiling point fraction. So these are your lighter fraction. These are your lower boiling point fractions. This will be your less viscous. Oops, I better just move that down a little bit. And there will be your less viscous, there will be the more flammable fractions. These are all properties as stated in the particular topic. And it's true for the fractions, they are further up at the top in the separating in the separating techniques, which is fractional distillation, fractionating column, as we do fractional distillation of crude oil. So butane has shorter number of carbons. This is just 4 carbon chained. This is 8 carbons chained in a molecule. So 4 carbon versus 8 carbons. The longer carbon you are, the longer the chain, the stronger is the intermolecular force. If you have stronger intermolecular force of attraction between the molecules, you're going to need slightly more energy to break the force of attraction. Therefore, you're going to have higher boiling point further down in the fractionating column. So boiling point of octane is going to be higher than the 4 carbon butane there, as you have stronger intermolecular forces, need more energy to break as a result. Question 37, we have propane and also chlorine. We see that this is an alkane. We know that alkane undergo very few reactions. The first one of which is your combustion. We are not reacting with oxygen, so it's not really combustion here. The second reaction, which is relevant to this question, will be substitution. And this is substitution with chlorine, so you do need UV light, which is ultraviolet light. If you do physics, you will know that this is of quite high energy and just next to the visible light region, but before the gamma light region. So what happened in a substitution reaction? You need to know the definition of a substitution reaction. Basically, substitution is replace one atom with another. So you're going to replace the hydrogen with the chlorine. So we can see that propane is an alkane. So alkane there is again going to have CnH2n plus 2 general formula. So for n equal to 3, you're going to put 3 times 2, which is A6. 6 plus 2 is going to give you 8. So there's going to be C3H8 and not C3H6 there. So A is out. And the C3H8, so all of them are fine. And we are never going to get hydrogen gas in a substitution reaction because we are just removing one H, just substituting one hydrogen with another, not hydrogen, but with another chlorine atoms. So we're just having 3 hydrogen to begin with, and now we have 1 carbon there. That is not correct. There's no substitution. You have broken carbon-carbon bond there. And having done that, D must be the only answer because replace one hydrogen on the CH with 1 chlorine atom, and then to form your CCl. But then your H comes off, and then the ClCl from the Cl2 molecules. That is how chlorine exists as a molecule, diatomic molecule, as an element, like that. And then you're going to have 1 more chlorine out and 1 more hydrogen out, forming the hydrogen chloride, which of course all of these are not dissolved in water. They are not hydrochloric acid. You will call this hydrogen chloride. Name the other product. This is a gas, as it is a pure substance here, and there will be hydrogen forming a single covalent bond and chlorine forming a single covalent bond, as chlorine has got 7 electrons in the outer shell. Therefore, you just need to share 1 of your dot, and you still have 6 more dots on the chlorine, but hydrogen just share your 1 and only electrons to get 2 electrons in the first shell, completely fill out the shell. On the other hand, we can think about chlorine and chlorine molecule also having, single covalent bond, but on both the chlorine atom, there will be other electrons that are not used for bonding. Make sure you know how to count the number of electrons that have been shared and the number of electrons that are left on each atom for this kind of correct dot and cross formulation there. In this question 38, we have propanoic acid. So we know propanoic acid is a 3-carbon carboxylic acid. If you write out the structural formula, or if you draw it out, you will have CH3 add another CH2. Now that we have 2 carbons, we just need to add CO2H. This is our 3 carbon now. So 3 carbon altogether. You should be able to spot that 2 and 1 give you 3 carbon, 2 and 1 give you 3 carbon, but you see in the options C and D, 3 carbon and 1 carbon, 3 carbon and 1 carbon. So C and D are not correct because C and D are definitely showing you butanoic acid. There are 4 carbons, which means that it's butanoic acid, not propanoic acid. Now the next choice between A and B, the difference will come down to the formula of the salt. So having done the formula of the acid, if I actually display it out, how would it look like? COOH like this. So what actually happened is, we know that will give you partial dissociation, partial ionization of weak acid. It partially dissociates into H plus ions in solution. So if you get H plus, that means we're going to get O minus, because carbon form 1, 2, 3, 4, it's got no change on this carbon, but this oxygen will get a negative charge as a result of the hydrogen having no electrons at all. So both the electrons in the OH bond goes to the O minus there. This is what you call propanoate ions. Well, we know when you form acid, when acid forms salt, the H plus of the acid get replaced by another cation. In this case, it's the calcium 2 plus as a group 2 metal. The oxidation number when they form compound will be plus 2, because they're going to exist as plus 2 cations when they form compound. So CH3, CH2, CO2 minus. Looking at the charges of the ions, that's going to give us the valency, their combining power. And then we do lowest common multiples, because the objective is very simple, cancelling out the charges. Plus 2 does not cancel out minus 1. So instead what you need is 1 of the 2 plus, and you need 2 of the propanoate. Each of the propanoate, if you draw it out and see it for yourself, you can see it's minus 1 and minus 1, such that the correct chemical formula will be calcium CH3, CH2, CO2 twice. Now what has happened here is they put the propanoate first, and that is fine, but you must have 2 of them. You must have 2 of them and not 1 of them, and therefore B must be the correct answer there. Question 39, we have which formula is the same in methanol. So methanol is a 1 carbon alcohol, so you can draw it out if you want to. This is display formula. I'm just going to draw structural now from this point onward. So CH3, CH2OH for ethanol, CH3, CH2, CH2OH. All I've done is I've added another CH2, I've added another CH2 as I go in this homologous series. So they are the same homologous series. They have similar chemical properties as they are all alcohols. They all have the same general formula, which is CnH2n plus 1 OH. Looks like alkane, but you replace one of the H of alkane with OH, therefore it's no longer 2n plus 2, it's 2n plus 1. Replace one of the hydrogens of your alkane, and you replace it with one OH. Now you're left with 2n plus 1 there. In terms of empirical formula, they will never be the same, I think, because there will be CH4O, and this is C2H6O, C3H34567 all of them you can see has only 1 oxygen. You cannot get any simpler, because that is to do with the simplest whole number ratio of atoms as stated in the year 9 syllabus. Definitely different empirical formula, because you cannot simplify them any further. Their general formula is all the same, as they belong to the same homologous series, having the same functional group of OH there, which make them alcohol. Their molecular formula is the same as their empirical formula, but then you can see that they are definitely different there, and the structural formula are different as you keep on adding CH2 to each member of the homologous series as you increase the number of carbon there. Well, their physical property will be different. Homologous series compounds in this particular order with more and more carbon, your melting point, your boiling point is going to increase due to stronger intermolecular forces, as these are all simple covalent molecules. You have more carbon, you have extended the chain, you have more total number of electrons in the molecules, your intermolecular forces between the molecules get stronger, your boiling point gets stronger there, get higher there. Question 40, the last questions in this particular paper. Ethene reacts with water. A bit dodgy, because we really think about this idea of steam, and this is under suitable conditions. We do know that ethene reacts with steam. That means your water needs to be in a very high temperature. That's around 300 degrees Celsius at quite high pressure. You also need a catalyst that is concentrated, H3PO4, also known as phosphoric That is wrong. Phosphoric 5 acid is your catalyst, that is in the worded form with the correct Roman numeral for the oxidation number of phosphorus there. And of course, you're going to get ethanol, and that is the whole idea, adding H and OH across the carbon-carbon double bond there. So this reaction is a redox reaction. Not entirely correct. The hydrogen is +1, the oxygen is -1, the hydrogen is +1 in ethene. Now you're going to get hydrogen +1, oxygen -2. You can work things out, but this will definitely not be a redox reaction, as you're looking at this carbon gaining hydrogen, but this carbon gaining oxygen, so it doesn't quite make sense, does it? It's not really redox, to be honest. In terms of redox, we are looking at oxidizing agent, so things like KMnO4, which is acidified, purple to colorless, but water, even in the gaseous state, is not going to be your oxidizing agent, so it doesn't quite make sense there. The reaction produces two different products. That is not true, is it? No, that is not true, because this is an addition reaction, defined addition reaction, as stated in the syllabus. In an addition reaction, you get only one product. Why you only get one product? Because the two reacting molecules combine together. This and this combine and add together to give you only one product. So B is wrong there. The reaction occurs when the ethene gas is bubbled into cold water. Cold water is not wrong because, it's not correct. It's not correct. So it's not bubble because we don't have any solution. Like I said, this condition, 300 degrees Celsius, is going to be H2O in the gaseous state there. So C is definitely wrong there. So A, B, and C are wrong. D is definitely correct. The product of this reaction, the product means there's only one product, so that is fine, because addition product from two reacting molecules that added together. In terms of the MR, so we're looking at CH3CH2OH. If you add that up, that is 12 plus 3 times 1 plus 12. I better just add up the carbon, to be honest. So there's just C2H5OH. That will make my life easier. 12 times 2 for the two carbons, and then 6 hydrogen, 6 times 1, and then 1 times 16. Pressing that into your calculator, 12 times 2 is 24, plus 6 times 1 is 30, plus 1 times 16, this gives me 46. This is the correct MR for ethanol, which is your final product of this addition reaction. D must be what we are looking for there. And that's it really, 40 questions for these particular tutorials for this. It's not an end of the exam. It's just for a pretty early exam in the year. This is a February 2023 school level exam, and hopefully the rest of the tutorials have been helpful to you. Don't forget to click the button on the bottom right of this particular video and all the other videos to subscribe to my videos. Leave a like if it has been useful, and do share the channel with your friends, chat group, juniors and seniors, and other people, and check out other useful topical playlists as well. Thank you for watching. Do follow me at ptet.chemistry, ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. I'll see you in the next tutorial video. Thank you for watching again.